Okay, good morning students. In this lecture of VLSI system design, we will discuss the topic comparator of our CMOS subsystem design unit. This one is the unit number 4 of your VLSI system design syllabus, and here we are discussing about comparator. What is the mean of comparator and how can we design it? Okay, this theoretical portion is from your Neil Wester book. According to it, according to it, unit number 4 of your According to it, the comparator circuit is nothing but a digital circuitry, is nothing but a combinational circuitry that is used to design any circuit that is responsible to compare the two different numbers. Okay, suppose I am considering one number as a and another number as b. So if we compare any two numbers, so definitely there will be the three different possible results. One is a equals to b, second one is b is greater than a, and the last one is a is less than b. Okay, these three results can be possible if we compare any two numbers. So to implement this type of comparator circuit, comparator circuit, according to designers, we can implement this circuit in many ways. Some designer can implement this circuit by using NAND gate only. Some designer can implement this type of circuit by using NOR gate only. And according to designers, someone can design it by using the combination of AND gate, NOR gate, etc. Okay, so here I am taking a circuitry and explain you how it works. Here it is mentioned that it is possible to implement this circuit by using XOR gate, by using NAND gate, by using AND gate, and etc. Okay, these type of comparator circuitry, this type of magnitude comparator circuitry is responsible. This type of magnitude comparator circuitry is responsible to compare any two bits. If we consider the if we consider the number is binary, so there may be the two different versions of binary. One is unsigned and another one is signed. Okay, one is unsigned binary and another one is signed. That means this type of comparator or any comparator can be works in signed comparison along with unsigned comparison according to requirement. Okay, this one is the theoretical portion, in this comparator. This one is the theoretical portion in this comparator. Here it is given that this type of comparator circuitry is responsible to compare any binary number or digital number. Any AND gate, NOR gate, NOT gate combination can be used to implement any type of circuitry. Okay, according to the numbers, there are the three different results that can be possible. One is a is equal to b, another one is a equal to b, another one is a is greater than b, and last one is a is less than b. These three results can be possible if we implement the circuit, or if we compare any two different numbers. Okay, so the number of bit so the number of bit in number a and b uh, can be vary according to requirement. Here, suppose it is given that the a number is from a1 a2 at a3 and so on, and b number is from b1 b2 b3 up to bn. Okay, so it means that if a is of n bit and b is of n bit, a is of n bit and b is of n bit, so there are the two different number of n bits. So if we want to compare this type of two numbers, so definitely we use magnitude comparator circuitry there. Okay, Oh, this one is the truth table. This one is the truth table of your magnitude comparator. Magnitude comparator compare two different number. Here I am considering that a number is of 1 bit, b number is of 1 bit. So if the two number is of 1 bit, so according to truth table, because of this combination, four different combination, because of this a and b combination, four different combinations are possible. That is 0 0 0 1 1 0 and 1 1. And here you can see, in if you are taking the first combination, that is 0 0. If you are taking the first combination, that is 0 0, here a bit and b bit are equal. So at that time, in output side, a equal to b bit is active, and other bits are inactive. Here you, in the second combination, you can see the a is 1 and b is 0. It means that a is greater than b. So at that time, the first output represent the 1 and other bits are 0 at that time. Okay, so when we compare any two numbers, it means that when we compare any two numbers, so three different results are possible. One is a equals to b, another one is a is less than b, and the third one is a is greater than b. Okay, when we simplify this boolean function, so we get three different outputs. We get the equation of we get the output equation for three different combination. One is for a is less than b, another one is a is equal to b, and the last one is a is greater than b. The output is represented by using the symbol C, D, and E. If A is less than B, at that time we will get the output. We will get the output combination as A bar B. A bar B. Why A bar B? Because when A is less than B, that means this column. When A is less than B, at that time this bit will active, and according to when we consider the input combination according to this position, so we will get the A bar B in the output side. That's why this column represent the output equation A bar B. Same as A equals to B. In when we check the A equals to B column, at that time we find out the first combination is active. First combination is responsible for B equals to 0 and A equals to 0. So we will get the output A equals to 0 and B equals to 0. You can see some mistake is there in the truth table. Here last bit is also active, because here also in the last combination also a equal to 1 and b equal to 1, and the first combination a equals to 0 and b equals to 0. So in both positions, in first position as well as in last position, in both position a equals to b condition will fulfill. So accordingly we will get the output as a bar b bar plus ab, a bar b bar plus ab. When we simplify a bar b bar plus ab, a bar b bar plus ab, so a bar b bar plus ab, I will write it down here. Ab, I will write it down here. A will ab plus a bar b bar. This one is nothing but a XOR output. This one is nothing but a XOR output. This one is nothing but a XOR output. And we know that we can represent XOR output as the complement of XNOR. We can represent the XOR output as the complement of XNOR. So this one is the XNOR gate. So if we are taking the complement of XNOR, then we will get the XOR. Okay, so the second combination represent the XOR. Second combination represent a XOR b or a XNOR b whole square. Okay, okay. Now if you are checking the third condition, a is greater than b, at that time only this second combination will active. This second combination will active. So here we will get the output as a b bar. Here we will get the output as a b bar. Okay, here we will get the output as a, here we will get output as a b bar. Okay, so we can say according to the truth table, we will get three different output. And by using these equations, if we implement a gate logic, by using this implementation, if we implement by using this equation, if we implement a gate level design, so this gate level design is represented here. So this gate level design is represented here. This gate level design is represented here. This one is the gate level design, and it is made by using by the help of these three equations. Okay, here the first output, here the first output represent the condition for a is less than b, second one is represent the condition for a equal to b, and third one represent the condition for a is greater than b. It means that if you want a simple, one bit, if you want to make a simple one bit digital comparator, at that time how many gates are required? At that time we require two NOT gate, two AND gate, two NOT gate, two AND gate, and two NOR and one NOR gate. Okay, at the time we require two NOT gate, two AND gate, and one NOR gate for for the for implementation of gate level design of one bit comparator. Okay, so there are some more type of comparator also. So, one of them is equally comparator. What is the purpose to use equally comparator? Equally comparator is a circuit that is only responsible to check that the input numbers are similar or not. If input numbers are similar, if the input numbers are equal, at the time it provide the output only. Okay, it means that suppose I am considering a two different number, suppose I am considering a two different number, one is a and another one is b. I am taking one number a equals to 1011 and b equals to 1011. Okay, so at the time these two numbers are equal. Here the last bit represent a0, this one is a1, this one is a2, and this one is a3, and the same as this one is a0, b0, b1, b2, and b3. When we put these bit into this XOR output, into this logic gate, so we will get output as 1, so we will get output as 1, so we will get output as 1. it means that it means that it means that the magnitude comparator provide output equals to 1. The magnitude comparator provide output equal to 1 only when when the input numbers are equal. Okay, so this equally comparator is also one type of comparator. So if this equally comparator is also one type of comparator, it can be made by using it can be made by using this one is XNOR gate. Okay, this one is XNOR gate. There are four XNOR gate and one AND gate. Okay, we can check it by taking some example. We are taking a equals to 0101, and same as we are taking b equals to 0101. Okay, so this one is a naught and this one is b naught. So I am providing the bit combination here, a naught and b1. Now this one is a1, this one is b1, so I am providing input combination as a similar. We are providing last bit as 00. Okay, so this one is the XNOR gate, and we know that XNOR only provide output as 1 when the both inputs are equal. So because of this characteristic of XNOR gate is known as coincidence detector gate. So this XNOR gate provide output as 1, this also provide as 1, this also provide as 1, and this also provide as 1. It means that this AND gate, all inputs of these AND gate are 1. So we know that AND gate is making the multiplication of their inputs. So if all inputs are 1, so accordingly we will get the output as 1. Okay, so I think this equally comparator circuit is clear to all of you. Okay, now we are moving towards some different comparator. This one is the sign comparison. Okay, sign comparison. Why we use this sign comparison circuit, sign magnitude comparison circuit? Okay, we know that there are the two different type of if we want to represent any number, so we have two different choices. We can represent it by using signed, we can represent it by using signed form, we can represent it by using unsigned form. In signed form, signed form is already only responsible signed form is only responsible to represent any negative as well as positive number, but unsigned form is responsible to represent only positive number. Okay, so by using signed form we can represent by using signed form wait signed form is used to represent the negative as well as the positive number, but unsigned form is only used to represent the positive number. It is clear to all of you? Unsigned is only used to represent the positive number, and signed is used to represent the positive as well as negative number. Okay, so when we are when it is required to implement a sign comparator, so at that time we need to understand these 4 bits. We need to understand these 4 bits. One is C is represented carry out. Z is represented for 0 in for 0. When all bits are 0 at the time, this 0 flag will be active. The next one is N they equal to negative when MSB in the result, and the last one is V is the overflow bit. Okay, so the truth table for this comparison, for the truth table for the unsigned as well as for the signed comparison is shown here. Truth table for the signed and unsigned combination is shown here. Okay, you can check this truth table also. Now the magnitude comparator. Now we can understand magnitude comparator. We discussed all these theory earlier. Now I am explaining it by taking some practical example. Here I am here there are the 3 different cases. We all know when we compare 2 different bits, so 3 different cases are possible. One is A is greater than B, and second one is A is less than B, and the third one is A equal to B. I am taking each case one by one. When I am taking the first case, that is A is greater than B. When A is greater than B, so for this type of comparison, if we are taking 2 different bits, here you can see A is greater than B. For checking it by using magnitude comparator, first we have to take the complement of A. First we have to take complement of A, and after taking the complement of A, we have to add the one in the LSB side. We have to add the we have to add one in the LSB side. This one is the representation. This one is the representation. In simple words, here we are using a here we are using subtraction for comparing the 2 different numbers. Here we are using subtraction for comparing 2 numbers, and we know that for subtraction we have to take the 2's complement of any number. So here I am taking a 2's complement of A. How can we take the 2's complement? For taking 2's complement, first we have to find out the 1's complement. After taking the 1's complement, we have to add 1 in the LSB, and when we add 1 in the LSB side, then we will get the 2's complement of that number. Okay, so here I am taking the 2's complement of A. For this, first we have to take the 1's complement. For taking 1's complement, we have to flip all the bits. So 1 is converted into 0, and 0 is converted into A. Here you can say 0 is converted into A, and 1 is converted into 0. So we will get A bar equals to 0 0 0 1, and at the last we have to add 1 from in the LSB. When we add these bits, 1 plus 1 plus 1, so we will get 1 1. So 1 is presented here, and 1 will be the carry. Now 1 plus 0 plus 0, so we will get 1, carry is 0. Now we have to add 0 plus 0 plus 1, so we will get 1. Now here carry is 0, so 0 plus 0 plus 1, so we will get 1. Here no carry is, here no carry will be the in the output side. Here no carry will be the output side, so here we can write it as carry equals to 0. Now what is Z here? What is Z here? Because here input is anything. If the input is anything except 0, so at the time this 0 flag will be the 0. If the input, if the all bits are 0 in the answer, so at that time only 0 flag will be the will active. Okay, now yeah, here I am taking the second case. In the second case, here the A is less than B. For taking the condition, for checking this, we are taking one example A. Here you can see A is less than B. So for checking this condition, we have to subtract B with A. So for subtraction purpose, I am again taking the complement, and after taking the complement, we are adding 1 here. So here you can say, here the value of carry equals to 1. Here you can see the value of carry equals to 1. So it means that if we get the carry as 1, it means that if we get the carry as 1, and some output in after the addition, so the 0 flag will be the 0, and carry equals to 1. So this one is the condition. This one is the condition to get. This one is the condition to get A is less than B. And last case, when we are taking the last case, here you can say I am taking the 2 different numbers and all bits are equal. So for this comparison, again I am taking the complement of A and adding 1. So here you can see, after subtraction we will get all we will get the answer as 0 0 0 0, and no carry we found in the we found in the carry bit side, or we can say no carry we have found in the 5th bit. So here the carry out, here the carry out, here the carry out. Okay, okay, first bit will be the one, first bit will be the one. How this first bit will be the one? We are taking the addition 0 plus 1 plus 1. When we are adding these bits, so this one will be the 0 and we will get carry as 1. So 1 plus 1 plus 0, so sum is 0 and carry will be the 1. 1 plus 0 plus 1, so carry will 1 is 0, sum will be the 0 and carry will be the 1. Okay, so because of this we will get the carry output as 1, we will get the carry output as 1. And because the all bits are 0, so here the 0 flag will be the active, so here the 0 flag will be the active. So by taking the carry output along with a 0 flag, by taking the carry output and 0 flag, we can represent the four different condition for a equals to b, for a is less than b, and for a is greater than b. These conditions are represented in this table, these conditions are represented in this table. Here you can see when a equals to b, when a equals to b, here you can see when a equals to b, so at the time the z equals to 1, at the time z equals to 1. When a is does not equals to b, it means the other condition except last one, other condition except last one, z equals to 0. That means if you are taking the first bit as z, so the second bit, for the second condition it will be the z bar. Okay, if we represent this condition for the carry bit, so we can say if you are taking the first condition, that is a is greater than b, if you are taking the first condition, that is a is greater than b, so here we will get the carry output equals to 0, here we will get the carry output as 0, and for the other condition we will get the carry output as 1. It means that for a is greater than b, the carry output will be the 0, and for the rest of condition, carry output with its complement. So here this conditions is represented. Okay, so these four conditions is represented by these four conditions. By using this four condition, we are making a gate level design, we are making a gate level design. Here you can see the not gate. Here the port that consists of not gate, the port that consists of not gate is a port responsible to get the complement of a. Okay, so this last pin is a naught, this one is the a1, this one is the a2, and this one is the a3. Because we know that in this type of comparison, first we have to take the complement. So how can we take the complement? For taking the complement we need a not gate. So here not gate is the port from which the a input is provided into the circuitry. Okay, and we also know that at last we have to add one from each combinations. That's why here the third bit of any adder is the 1. So this one is the complement of a, here we will provide the b input, and from this pin we will provide the 1. Okay, so accordingly the output will be provided to the AND gate whose input is the complement. And this NAND gate, this type of AND gate is also known as this type of NAND gate is also known as NOR gate. When we represent this type of AND gate, so this type of AND gate can be represented by using NOR gate only. Okay, so here we can see we will get the three different output. One is a equals to b, another one is a is greater than b, and the last one is a is less than b. Okay, you can check all these conditions, by using this c out and z combination, such as I am taking the last case, here I am taking last case here when a and b are equal. Suppose I am taking the all bits are equal, suppose I am giving here all bits are equal, so at the time a equals to b, so at the time a equal to b, so when we will so at the time a equal to b. Okay, so when a equals to b, so we will get the carry out equals to 1 and z equals to 1, carry out equals to 1 and z equal to 1. Okay, we will see how this condition exists. So when all bits are equal, when all bits are equal, suppose I am giving 1 1 1 1 1 1 1 1. Okay, so the last bit of the last combination is 0. Okay, and this one will be the 1. So in the first adder we will get the input as 1 0 1. input as a combination and 101. So accordingly we will get the sum as we will get the sum as we will get the sum as 1, we will get the sum as 1 and the carry as 0, we will get the sum as 1 and the carry as 0. Okay, we will get the sum as 1 and the carry as 0. Clear? Okay, here you can see, here you can see 101 again, the combination repeats 101 again. Wait, here we can, when two inputs are 1, so sum will be the 0, sum will be the 0 and carry will be the 1. Okay, sum will be the 0. Okay, here we will get the sum, here we will get okay, here we will get, wait a while. Okay, after the addition, here input is 1 because these bits are 1, so this one is replicated here, but because this not get 1 is 1 will be the complement, so we will get 0 here. Now the third bit is 1, so we will get input combination as 101. So when we are putting input combination as 101, so we will get the sum as 0, sum as 0 and carry as 1. Now same condition will occur here, 101. So again the sum as 0 and carry as 1, again sum as, again sum as 0 and carry as 1, again sum as 0 and carry as 1. It means that we will get C output as 1. Again we can see C output as 1. We can say this last condition is represented here, C output equal to 1. Now when these four inputs, when these outputs, when the output sum equals to 0, we will provide to this AND gate. So because of this bubble, these all 0 0 will be converted into 1 1 1 1. So when these 4 bits are 1, so we will get output as 1. It means that when C out equals to 1 and Z equals to 1, so this condition is only occur when A equals to 1. Okay, so the gate level structure, so the gate level structure for this type of design is shown here. Same case, if you check the by if you check this gate level design by taking this second case, so at the time you will get the carry out equals to 1, you will get the carry out equals to 1 here, and at that time you will get the Z equals to 0 here. And when you put the, when you put any practical number in where A is greater than B, so at that time you will get C out equals to 0 and Z equals to 0. At that time you will get C out equals to 0 and Z equals to 0. That means you will get the output equals to 0 from this port and output equals to 0 from this port. Okay, so this one is the gate level structure for this comparator. So this one is the gate level structure for this comparator. In your Neil Weste book, in your Neil Weste book, in your Neil Weste book, this combination is also given here. This same diagram is also given here. This same diagram is also given here. You can see the three different output conditions is given here. One is A equals to B, one is A is greater than B, and one is A is less than B. Same as the combination that is given here. Same as the combination that is given here. So I hope you all understand this topic, magnitude comparator very well. So thank you so much. In the next lecture, in next lecture we will study 0 1 detector. Okay, thank you so much.